In the last video, we talked about pure silicon and doped silicon. But here's the thing. If we try to analyze semiconductor devices by thinking about every single atom or bond, that's just not gonna work. It's way too complicated and inefficient. So instead, we use a simplified big picture approach. We think in terms of charge. Now let's start with something really fundamental. The total charge of a solid must be zero. Why? Well, in pure silicon, it's obvious. Every atom is neutral, so the whole material is neutral too. But what about doped silicon? You might think N-type has extra electrons, so it should be negatively charged. Or P-type has extra holes, so maybe it's positive. But actually, no. The dopant atoms we add, like phosphorus or N-type and boron for P-type, they're neutral atoms to begin with. Even after they donate or accept an electron, they just sit in the crystal as fixed ions. So we didn't create any net charge, we just shifted things around. Let's write this out step by step. The total charge, Q, in the material comes from three parts. Q holes plus Q electrons plus Q fixed equals to zero. In other words, we say Q mobile plus Q space. Q space is just another word for Q fixed, and Q mobile is the sum of Q holes plus Q electrons. Now from electrostatics, we know that Q equals to integral rho dV, so that means holes for holes, Q holes equals to Q integral Px dV, and for electrons, it is Q electrons equals to minus Q integral Nx dV, and fixed charges, which called space charges, Q space equals to Q integral Nd plus x minus Na minus x dV. And when we add all of that up over the entire volume, the total charge comes out to be zero. Q equals to integral Qp minus Qn plus Qnd plus minus Qna minus dV, and this term will be rho total, and Q total equals to zero. So again, the whole material stays electrically neutral. But here's the important part. Let me explain this. Just because the total charge is zero doesn't mean charge is zero everywhere. In different regions of the device, the charge density, rho x, rho total x, can vary. For example, near p-n junction, you might have more positive ions on one side and more negative ions on the other. This imbalance leads to E field inside the device. That's where the Poisson's equation comes in. And let me write Poisson's equation. The Poisson's equation is this. Here rho is rho total, so it's basically just this. And so if there's a region with more holes or fewer electrons or uneven doping, then rho x becomes non-zero. That gives us potential phi x, which can use to calculate some electric field, Ex equals to minus gradient phi x. And that's and that electric field, that's what controls how charges move inside the device. So here's the big idea. Instead of tracking atoms, we track charge density. We plug that into Poisson's equation. We get the potential and the field, and that's how we understand the physics of semiconductors.